laser ablation load. Yeah, okay, recording, sorry. So which is isotope-selective laser ablation loading of trapped barium ions. So first, what is laser ablation ion trapping? So thanks to sign up. So you, he already introduced what is an ion trap. So we have an ion trap in a vacuum chamber over here. So this is the basic forward trap that you have seen in Sinap's talk earlier. And we have these two lasers that I'll go into later. So we have a forward trap over here, and we have a barium chloride target over here. So we are working with barium in its compound form. So this gray piece over here is basically a metal cup, and this white part over here is the barium chloride salt. So yeah, it's basically a cup that holds the salt. And what we do is that we send a high energy pulse laser onto the target. And with enough high enough pulse energy, it will ablate it and then sublimates the material on the target. And barium atoms will actually come flying out. So as it flies out and it reaches the center of our trap, it gets it sees these two lasers, and what these two lasers does is this. So there's this first excitation laser which brings it from the a neutral barium atom from its ground state to its first excited state, and then this second laser brings its first excited state to the ionization limit, and so the atom gets ionized. So once it gets ionized, it becomes an ion. It sees the electric field of our trap, and it gets trapped in our ion trap. Ion trap. So this is a picture of what trap barium looks like in real life. So yeah, and this is the complete picture. So we ablate it, generate the atom plume, and then we ionize it, and then it gets trapped. So what we have here is basically a top view of the diagram that you saw earlier. So this is so you have a clearer picture of how the lasers and the components are configured. So the first, what's important to know is that the first excitation laser is perpendicular to the atom plume. So we have our target over here, and this is the first excitation laser. And this is important because to minimize Doppler effect from the flying atom. And in our trap, we have two targets. So one is the high volume barium chloride target, and the other one is the low volume one. So for the high volume barium chloride target, we fill it with natural abundance barium, meaning barium with isotopic composition that you can find naturally. And then the other one, this is low volume target. It is enriched with barium 133. And and so this is what we have in our trap, and I'll go into that later. So why are we loading this way as compared to the more traditional and pioneering method of using oven loading? So there are a few lists of advantages, but we just be focusing on the two major ones. So the first is that with laser ablation, you can work with the element that you want to load in compound form. And for barium, it is very convenient to be able to work in its compound form because, as you know, as you might know, barium oxidizes very quickly and very easily when you expose it to air. So during assembly, it could be difficult if you're not working with it in its compound form. And for some more exotic isotope, so let's say barium 133. Yeah, so barium 133 is currently rising in popularity as a trap ion qubit right now. So if you want to trap barium 133, we can only get it in its compound form. So if you want to trap barium 133, you have to use laser ablation, and yeah. So and that's one of the major advantages of using laser ablation. And then the second major point that I want to highlight is isotope selectivity. So this is unique to the two-step photoionization process and not really unique to laser ablation. And why we have isotope selectivity, and this is because of this first excitation laser. So for different barium isotopes, the excitation energy to the first excited state is actually different for different isotopes. So by tuning the frequency of the first excitation laser, we can selectively ionize the atoms or the isotope they want to trap, and thus we have isotope selectivity. So with this, we can work with non-enriched targets, which makes life easier, and you can just put a lot of material on your target. So for the first part of this talk, I'll be focusing on the high volume barium target. If you recall, it is this target over here, which has the natural abundance of barium. So this is what it looks like in real life. So it's basically a metal cup, and then the white part over here is the salt. So the way we prepare is just mix the barium salt with water, then just lather it onto into this metal cup, and this is what it looks like in our trap. And yeah, so since it is a natural abundance barium, it has the natural composition, isotopic composition, which you see in this table over here. So yeah, it is most abundant in barium 138, and it has some 137 as well, and then we have the other isotopes. And we are using this target mostly for loading barium 138 and barium 137. So right now, we want to load with laser ablation. We want to figure out, okay, at what ablation laser fluence is enough to generate the atom plume. So that is what we do. So over here in this graph is the fluorescence of the neutral barium atoms. So we send the first excitation laser to fluoresce the atom plume. And these blue dots over here, yeah, it corresponds to the neutral fluorescence. And if you look at this graph, at about 0.2 joules per centimeter square, it starts to generate noticeably the atom plume. And if you increase the fluence even more, it rises, and then it sort of saturates at around 400 counts for our setup. And then the other thing that we investigate is also the point where ablation generates ions directly. So at high enough, if your ablation laser has high enough pulse energy, you can actually sublimate the target and generate barium ion directly, and not requiring the photoionization lasers. So this threshold is found to be about at above 0.25 joules per centimeter square. So these green dots over here are the fluorescence of the barium ions. So yeah, so this is the fluorescence count of the barium ions versus the fluence, and we see that above 0.25 we start to generate barium ion directly from the target. So these are the two thresholds that we find. So we know the fluence, but actually, if you have a fresh target and you send the fluence that is supposed to generate barium atoms, if you have a fresh target, actually you will not get any neutral barium atoms from it with this pulse energy. We find that you need to increase it significantly to some higher pulse energy first. So in our case, we find it to be 0.7 joules per centimeter square. And only then you will start seeing neutral barium fluorescence, and the fluorescence signal will rise and through about hundreds of pulses at this pulse energy, and then the count will stabilize. And then once it is generating barium atoms at this pulse energy, if you go back to this low pulse energy at 0.2 joules per centimeter square, then you will see barium atoms being generated as well. So we call this process conditioning. So for a fresh target spot, we need to send high pulse energy to do something to the surface. We are not sure what is happening, but this is what we see. So we could be our conjectures is that we might be getting rid of the surface contaminants, or maybe changing the surface profile so that it is more directional. We are not sure, but this is what we see. So once you have an activated spot, we are also interested in finding how long it lasts. So at 0.2 joules per centimeter square, we find that a fresh spot lasts about 10,000 pulses. So if you look at this graph over here, this is the neutral barium fluorescence count versus the number of times we send pulses to the same spot. And these different color lines are for different spots. So if you see some drop off at about close to 10,000, some grow after 10,000. Yes, so on average, it is about 10,000 pulses when it drops off, and you do not see neutral barium fluorescence anymore. And the interesting thing is when we see this, if you look at the target by eye, we see that actually the salt is still present, and the spot actually can be revived again, so that it produces barium atoms again by conditioning it again at high pulse energy, meaning we send high pulse energies again to the spot that for about for a few hundred pulses, and then if you go back to this low pulse energy, it will start fluorescing again. So if I go to high pulse energy over at this point, you will start fluorescing again. So yeah, again, we know that this happens, but we are not sure of what is really happening. So to characterize the atom plume, what we have performed this time resolved fluorescence spectrum measurement as well. So what we have here, this vertical axis is the frequency of the first excitation laser, and this color scale is the fluorescence count. So and this time axis over here is the time from when the ablation laser hits the ablation target. So what we have here is essentially time slices of the neutral barium fluorescence spectrum, and you can see that at earlier times, so meaning the faster atoms. So at earlier times, the atoms that reach the trap first are the faster ones. You see that there's a frequency shift, a blue shift of the spectrum, and then at later times you see that it converges to some asymptotic value, and this is due to Doppler shift because of our faster atoms. It has more Doppler shift, and so from this measurement, by integrating over the slow atoms, we can get the fluorescence spectrum of barium, and we can actually resolve the fluorescence peak of the different isotopes. So this means that we should be able to selectively load the isotope that we want by parking the first excitation laser frequency at the isotope peak that we want. And then by integrating over the spectrum, we can get an arrival time distribution of the atoms as well. And then from this, we can calculate the velocity distribution of the atoms, and this is what it looks like. And from here, we find that the average temperature of the atoms is very high. It's about 30,000 Kelvin, which is much higher than ablating metal target, which gives you about 5,000 Kelvin. And what's notable is that even though the average temperature is so high, we still have enough slow atoms that we can resolve the peaks and for trapping as well. So we have seen that we can resolve the isotope peaks. So we should be able to trap selectively. So what we do is we have done a isotope selectivity trapping experiment for barium 137. So what we do is we park the first excitation laser frequency at this barium 137 peak, and then we pulse we send a ablation pulses, and then we try to trap. And then for each trapping attempt, we will check for the ion fluorescence for each isotope by tuning the frequency of the lasers that is responsible for ion fluorescence. So we check for each isotope, and so the caveat is that we could not check for the barium 135 fluorescence, and that's because we haven't figured out how the frequency configuration to get barium 135 fluorescing yet. So we can check for these are the even isotopes 137, 138, but not 135, unfortunately. And in these experiments, we trapping 378 times, and then we managed to trap 32 times. And out of the 32 times, we see that 30 of them are barium 137. So this gives us a selectivity of 94%. But this is noting that we could not check for barium 135, and the 135 peak is actually close to 137. So when we do not trap anything, we could be trapping 135 as well. So this is an overestimation. So it's an upper bound of the selectivity estimation. But if you compare the selectivity of barium 137 compared to barium 138, so 137 has 11% abundance, 138 has about 72%. It's definitely much more selective towards barium 137 than barium 138, and barium 138 we could see it if it is trapped. So we definitely have a positive selectivity. And but for a more definitive experiment, for more robust experiment, we will be trapping an ion chain, and then we will set the frequency to fluoresce barium 137, and we will check for any dark ions that we see. So this should be a more robust method to get a more accurate figure of the selectivity percentage in the future. So we performed the selectivity test for barium 138 as well. And then for this experiment, we did it the more robust way, which is to trap a chain and then check for dark ions if there's any. So what we see here is that is that at low enough pulse energy fluence, we can get very good selectivity, which is 100% over here. And as we increase the pulse fluence, we see that the selectivity starts to drop off, meaning we start to see dark ions in our ion chain. And it could drop below the 72% of the natural abundance, which leads us to suspect that it could be the dark ions could be something other than just barium ion. It could be some other species or molecules as well. So this is to be tested, but the takeaway is that at low enough fluence, you can get very good selectivity. Now we'll be moving on to the low volume target, which is this one over here. So this one is the one that we want to use for trapping barium 133. And it is low volume, which is in the order of micrograms, because barium 133 is radioactive. So if you don't want to get cancer, you cannot put too much onto it. So it has to be low volume for safety reasons. And what we find is that we could not look with the two-step photoionization method, and so we tried using the method that the UCLA group is using. So UCLA is the group. The UCLA group is the group that is the pioneering group that is trapping barium 133 for qubit experiments. So what they do is they use a direct ion loading method, which sends a much higher pulse energy to the target to generate barium ions directly. So it is about an order of magnitude higher. And then they will time the time where they turn on their trap voltage to trap the ions as they fly towards and into the trap center. And what we find is that, okay, we can trap the barium 138, but the loading efficiency is pretty low. And after about 10,000 pulses, we could not trap anymore. And unlike the previous target, we cannot revive the target spot at all. And we suspect that it is just depleting the target spot of the barium salt. And so the target is not viable as it is right now. And we suspect that the main missing step in our recipe is that in the UCLA group heat treated their target to about 1000 degrees Celsius. And we suspect that this likely impregnated the barium into the substrate, and it adheres more nicely onto the target. And we suspect that for hours, due to not heat treating it, when we blast it with our ablation laser, it just flakes off and blasts off from the surface, and just deplete the material from the target. So we are doing a separate set of experiments to test this as well. So for this separate set of experiments, we are trying to develop a viable preparation method for preparing micrograms of barium salt that we can still load. So we are trying different heat treatment methods and also different substrates as well. And over here is a picture of a thin layer of barium chloride salt, although this is natural abundance, so it is in milligrams. And although it is in milligrams or micrograms, it is still much thinner already compared to the high volume target that we have in our trap. So what we do first is that with this target, we don't heat treat it, and then we test our hypothesis, which is just ablate it with our conditioning pulse energy. And what you see here is what I described earlier, which is when you're conditioning, the neutral fluorescence signal, you will rise and then after a few hundred pulses, you stabilize the neutral fluorescence. And what we see is that after about 12,000 pulses, the signal goes away. And when we check back with a microscope, this is what we see. So this dark chrome color parts over here are actually the barium chloride salt, and this refractive part is the metal substrate that it sits on. And this dark spots over here, yeah, these spots over here, the circle in green are the ablation spots. And you can see that at the edges, it is cleaned off, so you can see directly the metal surface underneath. And at the center, we can see this black charring mark from the ablation. So from here, we see that, well, yeah, from the microscope, we see that, yes, it's confirmed that the ablation spot is indeed depleted of the barium chloride salt. And in addition to this, we also see that after doing this experiment, at the bottom of our vacuum chamber, there are these fractured off barium chloride salt as well. So yeah, so it seems that if you do not heat treat your target, as you ablate it, it really does just blast off some barium chloride flakes, and then it just fall off on into a vacuum chamber as well. So this is likely why our low volume target was not working. So yeah, so it seems that we need to heat treat our targets, and that is what we did. So we tested this on a palladium substrate. So we just heat treat the salt on a palladium target. So the heating method that we tried is just by resistive heating. So just passing current through it and heat it until the salt melts, which you see over here. And then if we look at it under a microscope, this is what we see. So these white parts over here are the parts with the salt. And you can see some scratch marks over here as well. So these scratch marks are our attempt at trying to see if it flakes off easily after heat treating it. And yeah, from what we have seen, it does not flake off easily, and you can see these marks over here because it is bending the metal as we scratch it. And if you look at it with this X-ray spectroscopy, X-ray energy spectroscopy, if you look at a low concentration spot, yeah, it does confirm that these white parts are the barium chloride salt. So when you look at the low concentration spot, the barium and chlorine composition is indeed low. And when you look at the high concentration spot, yeah, they are high as well. And if you look at here, the oxygen content is high, and that's because well, we do not have a method to heat it and then put it in a chamber or and then test it all in vacuum yet. So it has oxidized somewhat during this process. Yeah, so this is where we are at right now, and we still have not tried looking for neutral barium fluorescence from this target and trying to load from this heat treated target yet. Yeah, so in summary, we have figured out the threshold of the laser fluence to generate barium atom plume, well, at least from the non-heat treated target. And then we find that the temperature is very high after you ablate it, which is about 30,000 Kelvin. And we can resolve the barium isotopes peaks, the different isotope peaks from the neutral barium fluorescence spectrum. And so we should be able to selectively load, and that is what we see as well. So barium-137 has a selectivity of 94%, but this is something that we could not check for. Well, it is not the more robust method. And then with barium-138, yeah, it is. We find that we have very good selectivity if you have low enough pulse energy. And we have some initial tests on trying to prepare a low volume barium source target as well, and it shows that we need to heat treat it. Yeah, so this is a summary, and this is our team. Yeah, and yeah, thanks for listening. I welcome any questions if you have.
All right, thank you, Pei Jiang, for that excellent talk. Are there any questions from the audience?
I have one.
Okay, great.
How well does I mean, when you get such high temperature ions, I presume your cooling, your normal laser cooling systems are not at all designed to work with that high temperature, or can they work fine?
Yeah, those high temperature atoms, I suspect that they are we cannot trap them to begin with, because there's a limit of because whether we can trap these ions or not is okay. The ion trap has a potential barrier, so these ions over here are higher than these atoms over here are definitely higher than the potential barrier of the trap. So they will just fly through your trap. So the ones that we can trap is actually about 500, 500 meter per second over here. So these are the portions that we trap actually.
But could you, going a little bit maybe off topic, but if you wanted a medical application, if you wanted to have these radioactive ions or something, could you then channel them effectively? You could have lenses that will lens these ions into a beam and going in a particular direction or anything like that?
I don't quite get what you mean by lensing the ions into. Can you?
Well, with electromagnetic fields, could you? You've got this flux of high speed ions. Are you able to channel it into a beam or anything like that? Or do they come off in all directions, or is there some directionality with the?
Okay. They probably they probably are coming out in a conical direction. But the ones that actually we can pick which direction is the one that we ionize. So actually we can have directionality as well. Well, this is off topic, but what I'm saying is that okay, it could be coming out in a cone over here, but they are not ions. But once they are ionized, only the ones that are ionized over here will become ion. So we can direct the ones that we ionize, but not the ones that we ionize. Yeah. Do I hear another question?
I think that was just background noise. I'm not sure though.
I see. Okay.
So you mentioned that at a certain point you start getting barium ions directly. Are those? Maybe I'm a little confused. Are those by themselves a problem? Like are they just going off into the background? You don't really care too much about those.
I see. Okay. Yeah, they are not a problem if you keep your trap barrier turned on all the time, because or even if you have ions due to the potential barrier of your trap, they will just get diverted away from your trap. So they're not a problem.
All right. All right. Are there any other questions? If not, of course, we have a discussion period after the next talk with lunch. So if you think of anything, just hold on to it. I'd like to